Hey everybody, in this video we are going to learn how to describe planes in 3 dimensions. So to begin with, let's go back to the 2-dimensional analog of a plane, the line. What does it take to determine a line? What determines a line in 2 dimensions? Well, 2 points will do. If you've got 2 points, there's only one line that goes through both of them. What do we need in order to write down an equation for a line in 2 dimensions? Well, if we know one point and the slope, that ends up being enough. In that case, we can use the point-slope form of the equation for a line, which is very handy. With a little bit of algebra, you can make it look, you can turn that into the slope-intercept form, but in this case, and in a lot of other cases, really, the point-slope form is very nice. If you have trouble remembering the point-slope form, with a little bit of algebra, you can see that it's the same as this form here. And if you step back for a moment and think about what those terms represent, we'll recognize that it's really just a special way to write the definition of slope, if you like. Okay, so that's lines. What about planes? What determines a plane in 3 dimensions? Well, there are a few ways you can do it. Having 3 points that aren't all on the same line, that'll uniquely determine a plane. Or if you've got a line and a point that doesn't lie on that line, that uniquely determines a plane. Or if you've got 2 intersecting lines, those will determine a plane. Or if you've got 2 parallel lines, that also determines a plane. But what about coming up with the equation for a plane? Well, it turns out one way to do it, we can do it with just a point on the plane and a vector that's perpendicular to our plane. If I've got those 2 pieces of information, then I can write down the equation for a plane. And so now we'd like to see how exactly that works. If we've got some point and some normal vector, then we'll be able to proceed. And so if I had any vector that lies in the plane, if I take the dot product of that vector with the normal vector n, we know we'll get 0 because those 2 vectors must be perpendicular. And so if I take, say, an arbitrary point with coordinates x, y, z, and sort of leave those as variables, then I can write down this equation. And make sure you take a moment and see where this vector on the left is coming from. Why is it I'm able to write that down? And why is the dot product with n then going to be 0? And from there, we can just expand out the left-hand side, and we get what's called the standard form of the equation for a plane. So remember, n1, n2, n3, these are known quantities for that normal vector, and x0, y0, and z0. Those are the coordinates of the point on the plane, so the only variables remaining are x, y, and z, and this gives us the standard form of the equation for the plane. With the standard form, we can also do a little bit of algebra and recollecting and renaming of some things and get to what's known as the general form of the equation for a plane. So let's practice for a moment. Take a minute to see if you can determine the equation of a plane that contains this point with this normal vector. And now also, what about figuring out the equation for this plane that contains these 3 points? We said earlier that 3 points was enough to determine a plane. So how is it I can take 3 points and determine the equation for a plane? I still need, for the method we just talked about, I still need a point and a normal vector. So is there some way I can get a vector normal to this plane out of these 3 points? There certainly is. I can figure out vectors that go between these points, and if I've got two of those vectors, they definitely lie in the plane. If they take us from one point on the plane to another point, that'll lie in the plane. And so if I've got 3 points, I can find at least 2 of those. And with 2 vectors in the plane, then how do I figure out a normal vector? Well, we can do that with the cross product. So if I've got 2 vectors, and be careful that I've got distinct vectors there, that one is not just the opposite of the other. If I've got those 2 vectors, then the cross product of those 2 vectors gives me a normal vector to my plane, a vector that's normal to both of them. That's normal to the plane since it's normal to 2 vectors that are in the plane. So take a minute and make sure you can find the equation of the plane given this information, and then we'll talk about it in class.